next topic in our course is two-port functions. Okay. Next topic in our course is two-port functions. So we are studying fourth module, right? So we have completed some topics in fourth module, and this is our next topic. It is two-port functions. Two-port functions. So if you see the previous topics, RC networks, LC networks, driving point impedance functions, all these things. So in the previous classes, what we were trying to do is we were trying to synthesize network. We were trying to synthesize network for driving point functions. If you see, so if you see the previous classes, we are trying to synthesize networks. Okay, we are trying to design the networks for driving point functions, either driving point impedance function or driving point admittance. So we have four forms. Okay, we have seen foster 1, foster 2, KVR 1, KVR 2. Okay, so the given function was driving point impedance function. So driving point impedance or admittance functions are defined for one port network. Okay, that means you are defining driving at one port. Okay, a pair of terminals, you are defining either driving point impedance function or driving point admittance function. Okay, so you are defining either driving point impedance or admittance functions at one port. Okay, driving point impedance or admittance function. I don't understand what. So driving point impedance or admittance functions are defined for one port. Okay, at one port we are defining. So two-port function. So for a two-port network, so what we have studied about two-port networks, a two-port network is defined by four parameters. Okay, so if you see all the various two-port parameters, what we have studied, there are four parameters. We have studied six sets. Okay, six types of parameters, but in each set or in each type we have four parameters. Like you take ABCD, okay, Z11, Z12, Z21, Z2. Okay, so two-port network is defined by four parameters, and in case of two-port network, so what we call transfer function. So what is the transfer function in two-port network? This thing. Okay, so T of S is V2 of S upon V1 of S. Okay. So in the previous classes, for the driving point functions, which is defined at one port network, we are trying to synthesize a network. Okay. So in this, from here, for two-port network, we are defining transfer function as this. Okay, which is nothing but this I have defined while studying about transfer functions. Okay, network functions or transfer functions. I think in the previous module, network functions or transfer function. While defining that, I have defined driving point functions as well as transfer functions. Okay, both are network functions only. So for a two-port network, the transfer, if I say transfer function for two-port network, it is this. Okay, what is that? Open circuit voltage ratio, V2 upon V1. This is your transfer function in case of two-port networks. Okay, filter networks are specified by open circuit voltage ratio. Okay, so two-port networks, filter networks, all these are specified in terms of this transfer function. Okay, so what is the transfer function? Voltage, open circuit voltage ratio. Okay, so what is the general definition of transfer function? It is Laplace of output upon Laplace of input with zero initial condition. Okay. So this is the transfer function in case of two-port network. Okay, two-port network, it is V2 of S upon V1 of S, right? So now in here, what we are trying to do is we are trying to synthesize network for this transfer function. Okay, so two-port networks are defined or specified by these transfer functions. Okay, now we will be given with the function T of S, V2 of S by V of N, V1 of S for a two-port network, and for that given function we have to design or synthesize a network. Okay, that is the difference between previous classes and now what we are going to study, right? So in the previous classes for driving point functions, you see all the forms driving point functions or driving point and impedance or admittance. But now for a two-port network, we are defining this thing. Okay, this thing as transfer function, which is nothing but open circuit voltage ratio, which is V2 upon V1. So here, if you see what is V2 and V1, V1 is the input voltage or source voltage. Okay. So V1 is this. Okay. V1 is the input voltage or source voltage, and whereas V2 is your output voltage or load end voltage. Right. Load voltage, output voltage is your V2, and transfer function is V2 of S upon V1 of S. Okay. So this is your transfer function for a two-port network. So if you see V2 of S upon V1 of S, we can express T of S, which is V2 of S, output voltage upon input voltage, V1 of S in terms of two-port parameters. Okay. So you can express V2 of S upon V1 of S or upon V1 in terms of two-port parameters. Okay. So this is open circuit voltage ratio, that is V2 upon V1 at I2 is 0. If you see, you can express T of S as 1 by A. Okay. So these are your ABCD parameters, and A is V1 upon V2 at I2 is 0, and V2 upon V1 is 1 by A. Okay. So transfer function. Okay, what is transfer function? 1 by A. Similarly, with the table given to you. Okay. So we have a table, conversion table between different two-port parameters. So from that table, you can write this thing, okay, V2 upon V1 as this thing, right? So minus Y12 upon Y22 or Z12 upon Z11. Okay, so try to remember this. Z12. So transfer function, which is V2 of S upon V1 of S, is equal to Z12 upon Z11. Okay, Z12 upon Z11. Z12 upon Z12. Okay. So for a two-port network, T of S is a transfer function. So for a two-port network, T of S is a transfer function. That is open circuit voltage transfer. Okay. This is your transfer function, two-port network. So our two-port function, it is a two-port function, or two-port transfer function, which is T of. So generally filter circuits. Filter circuits, you have a network. Okay. You have passive filters, active filters, passive filters. Take RLC. So you have a two-port network, okay, which is passive, and it is a filter circuit. It is a filter circuit. So filter means it that we are going to see. It allows some certain frequencies to pass through it, okay, through the circuit, right? So T of S is V2 of V2 upon V1. Okay, this is your two-port transfer function. Okay, for a two-port network, T of S is a transfer function, which is nothing but open circuit voltage ratio, and it is expressed in terms of Z parameters, Z12 upon Z11. Okay, remember this. So T of S is V2 upon V1, Z12 upon Z11. Okay, so this is about two-port function. So let us see. Now this function will be given to us. Okay, T of S will be given to us, and we have synthesized it. So let us see how do we do that. Okay. So zeros of transmission. So what are zeros of transmission? Like now this is your transmission function or transfer function, which is nothing but V2 upon V1, right? So V2 upon V1, right? So the input voltage is transferred to output, and the output voltage is V2. That is a input. So transfer function V2 upon V1 is right. Now what is zeros of transmission? Now this is a T of S is a transfer function. So you will have numerator and denominator, right? So you can write it T of S as P of S upon Q of S, right? Now what are zeros of transmission? So this, when you equate P of S to 0, that is your P zeros of transmission. But what is the meaning? Zero transmission. Okay, zeros of transmission means when T of S becomes 0, that is P of S equal to 0. So when T of S is 0 implies there is no transmission of voltage. That means your output voltage is 0. The frequencies at which zero transmission occurs. Okay. So there is no transfer of voltage from input to output. Okay. Okay, the frequencies at which zero transmission occurs. What is zero transmission? Zero transmission means you have input but no output. Okay, right? So you have input but no output. That is zero transmission. Right? So that is input is not equal to zero, but output is equal to zero. Okay? You have output zero, no transmission. So zeros of transmission. So zeros of transmission, which is nothing but T of S equal to zero or P of S equal to zero. Okay? Those are called zeros of transmission. You have input but no output, right? So input is not equal to zero and output is equal to zero, right? So those are called zeros of transmission. The frequencies at which zeros transmission occurs. Okay, that means you are equating numerator to zero. So now T of S you can express it as like this. Okay, P of S upon Q of S, and which is V2 of S upon V1 of S, which is also Z12 upon Z11 and 1 right? Now coming to that, we have to synthesize a network. Okay? So this we have to synthesize a network for this transfer function. Okay, so now for any network, okay, so the basic, right? So now we are going to synthesize two-port network for this transfer function. Two-port network for this for this transfer function. So for the stability of the network, the poles, okay. So I'm now next to two lines I'm talking about poles and zeros of this transfer function. Okay. Poles and zeros of transfer function. So the poles of transfer function are restricted to the left half of S plane, and these are simple poles on imaginary axis for stability consideration. Okay, that this we have seen. Okay, the poles of the system should be to the left hand side. It should be present in the left half of the S plane, and these poles should be simple poles if they are present on imaginary axis for the stability of the network. Okay, for this we have seen. Okay, for the stability, the pole should be in the left half of this plane. Right, so that is applicable to this also, right? It is applicable to this transfer function. Okay, and coming to zeros, the zeros of transmission can be anywhere in the complex plane, but right. So the zeros of transmission can be, it is zeros of transmission means I'm talking about zeros of this transfer function. Zeros of transmission can be anywhere in the complex plane, but for ladder networks, zeros are restricted to the left half of S plane. Okay? So zeros can be in the right hand side or left hand side, but pole should be left hand side, and they should be simple poles on imaginary axis. But zeros can be anywhere, but for ladder networks, if you take a ladder network, okay, what is a ladder network? This is your ladder network. Zeros are also restricted to the left of it. Okay? That means for a ladder network, you have poles and zeros to the left of it. Okay? So for a ladder network, zeros are present on the left of S plane, and poles are obviously present on the left of S plane for stability. Okay. So this is about poles and zeros of a transfer function. Of this transfer function for a two-port network. Okay, V2 upon V1. Right. So zeros for ladder network, this is important. So these are for ladder network, zeros are restricted to the left half of S plane. Now for a ladder network, if you see, poles and zeros both are on the left half of S plane. Okay. So now what is ladder network? This is your ladder network, Z1, Z1, Y2, Z3, Y4 in this way. Okay. This is your ladder. Now this is your transfer function for two-port network. Now we are going for this transfer function. We are going to synthesize ladder networks. Okay, what are these two types of ladder networks? RC ladder and LC ladder. Okay, so this function will be given to us. Okay, transfer function, which is two-port transfer function or transfer function, voltage ratio, open circuit voltage ratio or transmission ratio. So this will be given to us, and we have to synthesize a network. So we are considering ladder networks. So we are considering ladder networks, RC ladders and LC ladders. Okay. So we will see RC ladders today. So we will see RC ladders, okay, RC ladder networks for given transfer function. Now, so just basic 2 points we will try to understand. So zero transmission from when we say there is a zero transmission or no transmission. Zero transmission from input to output occurs when series arm is open. Suppose in your ladder network, series arm is open. So in your ladder networks, if series arm is open, there is no transmission of voltage from input to output. Okay. When series arm is open, there is no transmission. Okay. You can see here, because transfer function will become 0. V2 upon V1 will become 0. Right, because the series element is open. Okay. Similarly, when the shunt arm is short circuited, okay, let's see this highlighted portion. Suppose you have a shunt arm. Okay, in ladder network you have a shunt arm which is short circuited. Okay, which is short circuited. Then in that case also there is no transmission. Okay, transmission or transfer function will be 0. T of S is 0. V2 upon V1 is 0. Right. So these are the two. So this sentence is nothing but these two things, that is zero transmission. Okay, zero transmission occurs from input to output when series arm is open and when shunt arm is short circuit. Okay, but the case is same. Is right. So V2 upon V1 is 0 here because V2 is 0. It is short circuit. Right. When series arm is open and shunt arm is short. Right. So these are two basic things you should know. Right. Now coming to this transfer function. This is our transfer function, right? So P of S. So to synthesize network. So so this is what we are going to do. So T of S, P of S upon Q of S is given to us. Okay. So T of S, P of S upon Q of S, this will be given to us. So now, so we are dividing with a function that is Q of S. Okay. Both numerator and denominator, we are dividing with function Q of S, capital Q of S, right? So and this T of S, which is also equal to Z12 upon Z11, right? So now we are dividing with capital Q of S. Now how Q of S must be selected? So Q of S must be selected. Okay, there is a criteria for this. So how Q of S must be selected? Q of S must be selected so that this Q of S upon capital Q of S, okay, which is denominator, okay, is a positive real function, okay, which is nothing but Z11 if you observe. So this is Q of S upon capital Q of S, which is a Z11, okay, which is a positive real function. Or so you know we have studied that all positive real functions are emittance functions. So that we can use previous methods, okay, RC method, right? Because when you divide by capital Q of S, it should become positive real function Z11. So in that case, so your capital Z11 becomes Q of S upon capital Q of S Z12, which is your transfer impedance function. Okay, if you see Z11, it is a driving point impedance, driving point function. Z11 Q of S upon capital Q of S is a driving point function, specifically driving point impedance function. Whereas Z12 P of S upon Q of S is your transfer impedance function because it is Z12, right? So you should select Q of S in such a way that Q of S upon capital Q of S must be positive real function. That is impedance function. Okay. And there are other criteria for Q of S selection. So we will see, this is general criteria. Okay. This is general criteria, right? Q of S upon capital Q of S should become positive real, right? So in that case, Z11 becomes this thing, and your Z12 will become this thing. Transfer impedance. Now coming to, so we are first to synthesize or to realize tree of S. First, I am taking RC ladders. Okay. So let us try to synthesize T of S, okay, or given transfer function for RC ladder using RC ladders. Okay. So if you remember ladders networks, right? Ladders network, all the poles and zeros of a ladder network should be to the left of, should be to the left of the, be present in the left of S plane. Okay. So this is what I told you, right? So now if you see for realization of transfer, so first we are studying about RC ladders for the realization of T of S. Okay. So T of S will be given to you thus, and we are going to realize in terms of RC ladders. Okay. So now, so just like previous cases, so when transfer function is given to us, so we should first identify whether it is for RC ladders or whether it is like in previous cases, whether it is RC impedance function or RC admittance function. Okay. Like that, there are some conditions. Okay. So now T of S is given to us. So for RC ladder, so what are the conditions? So which we have seen. Okay, the poles of the transfer function of RC ladder networks should be simple and should be restricted to the negative real axis. Okay, this is common point. Okay, the poles of the networks, any transfer function, right, should be to the left hand side. Okay, and it should be simple if present on imaginary axis. But additional thing is for RC ladders, excluding origin and infinity. So I repeat the statement. So the poles of the transfer function of an RLC ladder network poles are simple and restricted to the negative real axis, excluding origin and infinity. Okay, that means you should not have pole at origin and infinity. Okay, for RC ladder, for RC ladder. So for general case, the poles should be to the left for any transfer. For the stability of the network, the poles should be to the left hand side and should be simple poles, right? But for RC ladders, there is one more additional condition, that is they should not be pole at origin and infinity. So that means you should not find any denominator at the denominator. You should not find any s like 1 by s. Okay, for RC ladder, because you should not have pole at origin and infinity for RC ladder. Okay, excluding origin and infinity. That means you should find denominator 1 by s plus 3, 1 by s plus 5, not 1 by s. Okay, like this is about poles for RC ladder and zeros. So for RC ladder, how the zeros should be, the transmission zeros. Okay, transmission zero means the transfer function zeros. Okay, are restricted to the negative real axis. Okay, we have seen for ladder network, it is to the negative real axis. Okay, negative real axis in the sense no zeros in the right hand side, right hand portion, or no imaginary zeros. Okay, so it should be purely real and it should be the negative real axis for RC network. Okay, so no zeros in the RHP, right half of S plane, and no imaginary zeros. Okay, there should be no imaginary zeros. Only the transmission zeros are restricted to the negative real axis. So overall, you can summarize that for RC ladder, poles and zeros should be to the left half of S plane, but there should not be pole at origin and infinity. Right? That's it. So that is about your RC ladder. So now T of S, P of S upon Q of S will be given to you. So now follow the procedure, right? So what is this procedure? We'll see. So we will express P of S upon Q of S in this way, right? Divided by capital Q of S. Okay. To synthesize, why we are doing this? To synthesize the network that you are going to understand, right? So P of S upon capital Q of S. Similarly, Q of S upon capital Q of S. Do it, and which is Z12 upon Z11. So what is the criteria for Q of S? We have seen this should be positive real function, and there for the RC ladder there are other criteria. That is, Q of S is selected such so that its zeros are on the which zeros. Q of S is selected such that its zeros. Okay, Q of S zeros. Okay, such that its zeros are on the negative real axis and interlacing with those of Q of S. Okay. So in the for a given transfer function, you will be having denominator small q of s. Okay. Now we have to select capital Q of s. How we are selecting capital Q of s? So such that its zeros, that is capital Q of s zeros, are on the negative real axis. Okay. That means real zeros, and interlacing with those of Q of S. It should be like, suppose small Q of S poles are 1, 3, 5. Then capital Q of S poles you can take 2, 4. Okay, capital Q of S zeros, that is you can take 2, 4. Interlacing. Okay, interlacing means the small Q of S zeros, small Q of S zeros, which are nothing but poles of T of S. Okay, and zeros of Q of S must be interlacing. Okay, interlacing means 1, 2, 3, 4, like as I do, right? So that is the first point. So now we know how to write Q, capital Q of S. One point is, and one more point, Q of S can have 0 at origin. Okay, capital Q of S, we can select that, like you can select 0 at origin for capital Q of S. Okay. We are dividing by capital Q of S. I'm talking about this. Okay, you can have 0 at origin, and the degree of the highest power of S. Okay, this is important. In Q of S cannot be less than that of capital Q of S, small Q of S. Okay. So in the whatever the term you are seeing here, so the degree of Q of S must be always greater than small Q of S. That is the meaning. The degree of capital Q of S should be always greater than the degree of small Q of S. So here it is mentioned, the degree of highest power of S in capital Q of S cannot be less than. Cannot be less than means it is always greater than the small Q of S. Yes, if you take this fraction, capital Q of S degree should be always greater than small Q of S. Okay, should be always greater than, right, or equal to of small Q of S. Okay. So that is, these are the two. So with these two things, we can write Q of S for a given problem. Okay. So that is, so suppose transfer function is given to us for a two-port network, and then you can choose capital Q of S. How we are choosing capital Q of S? So interlacing, zeros of Q of S should be interlacing to that of zeros of Q of small Q of S. And one more thing is, the degree of capital Q of S should be greater than the degree of small Q of S. These 2 points you have to remember for RC ladder. Okay. So we are going to solve a problem, then you will understand. And this is equal to Z12 upon Z11. So Z11 is capital Q of S upon small Q of S upon capital Z11. Okay. And now if you see Z11, after writing in this way, it is becoming RC impedance function, right? So it is becoming RC impedance function, denominator Z11 and RC impedance function, and you can realize RC impedance function with KR from 1, okay, which we are going to do that. Okay, so Z11 becomes Q of S upon capital Q of S, which is a RC impedance function or RC ladder. And now this is our transfer function. Here now for simplicity, like now this transfer function can be in different forms. Like in numerator you may not have zeros, right? And you in the numerator, and this transfer function can have zeros as well, or it cannot have any zeros. Like in numerator only constant may be present, right? Or in the numerator you may have only s square, s cube. Okay, so different possibilities are there. So first we are going to see when the numerator is constant. Okay, so the transfer function, so see, actually based on this transfer function v2 of s upon v1 of s, so different filter networks are realized. Okay, like you have low pass filter, high pass filter, band pass filter, and band stop filter. Okay, just by looking at transfer function, you can say, just by looking at this transfer function highlighted portion, you can say what kind of filter it is. Okay, low pass filter, high pass filter, right? So so what is a filter? I will explain you. So we are studying in detail. So just for now, you can understand that a filter is a circuit which allows certain types of frequencies. Okay, low pass filter in the sense, so it will allow lower frequencies up to, so, okay, it will allow, so a low pass filter will have higher cutoff frequency. That means it will allow all frequencies below higher cutoff. Similarly, band pass filter. If I say band pass filter, so it will allow frequencies within that band. Okay, that is for a band pass filter, lower cutoff frequency and higher cutoff frequency will be mentioned. So within that two cutoff frequencies, the signal will be high, and during other frequencies, signal will be low. Okay, so these are the filters. So generally, filter in the sense when we call a filter, then we are filtering the frequencies. Okay, so we are allowing certain frequencies to pass. So we have to design a circuit for that. Okay, so so the transfer function of different filters I told you will be different. Okay, so in the numerator, if you have only constant, it is called sum filter. Like if you have some constant in the numerator, so it is a low pass filter. If you have s in the numerator, it is a band pass filter. That you will study. So first case we are taking p of s is 1. Okay, if you take, to simplify synthesis problem, consider the case of all pole transfer function. Okay, so let us choose first p of s equal to 1. Okay, p of s is 1. Okay, so when you choose p of s is 1, then t of s, which is small p of s, upon small q of s, which is your transfer function, will become this, and this is the transfer function of low pass filter. Okay, low pass filter. Okay, low pass filter means it will have some higher cutoff frequency and it will allow all the frequencies below that. Okay, lower frequencies. It will allow just lower frequencies up to certain point. Okay, so that point is higher cutoff, high cutoff frequency. So the transfer function of low pass filter will be in this form. Okay. Now this transfer function is given to you, then it is in this form. It is a low pass filter. Okay. Now we have to synthesize low pass filter. Okay. Network. We have to synthesize network for low pass filter, and this is realized by. Okay. So now what is the procedure? Divide by capital Q of S. Okay. So the network is realized by small q of s upon capital Q of s. Okay, now Z11 becomes small q of s upon capital Q of s. Okay, if you see this, the numerator becomes 1, so Z11 will be same, right? The numerator is 1, right? So it is a constant, some constant. Okay, your Z11 will be the same as it is, and Z12. Okay, so your Z12, okay, which is this, it is realized. Okay, Z12 is obtained with a constant multiplier. So Z11 we are obtaining by this, in this way, Q of S, one capital Q of S, and Z12 is realized with a constant multiplier. So Z12 is a transfer impedance. So just if you determine that constant by comparing the network as well as transfer function, okay, at s equal to 0 or s equal to infinity, you are determining Z12. Okay. So and once you get Z11 in this form, try to express Z11 in KR form 1. So you know how to realize or synthesize network in terms for KR form 1. KR form 1, you know how to synthesize the network. And Z12 is realized with a constant multiplier. So we are assuming Z12 is some constant K, and it is obtained. Z12 is some K is a K, and it is obtained by comparing, right, by making s equal to 0 or s equal to infinity and comparing both network and transfer function that you are going to see. Okay. So RC ladder, so in RC ladders, now first what we are taking is, first case is P of s equal to 1, right? That is 1 by Q of s you have, which is a low pass filter. Okay. When you have a low pass filter, right, this thing, and for realization of this network or for synthesis of this transfer function, we are dividing by capital Q of s. Okay. Then you will have Z11, which is nothing but small q of s upon capital Q of s. Okay. From this, yeah, Z11 is small q of s upon capital Q of s. And your Z12, you are uh, you are realizing, or Z12 is simply obtained by determining constant k by k, determining constant k under what conditions? Under s equal to 0 or s equal to infinity. Okay. Right. Let us see. So let us see one example. You will understand. So RC ladders. So this is first we have to determine. So this transfer function is given to you. Okay. And this is transfer function for a two-port network is given to you. T of s is 1 by s plus 2 into s plus 5. Okay. Is given to you. So the first thing is 1 by, it is in this form, 1 by q of s. So it is a low pass filter. Okay. And for RC ladders, okay, what are the conditions? The poles and zeros should be to the left half of S plane, right? And there should not be any pole at 0 or infinity. If you see, there is no pole at 0 or infinity. Okay, you have pole at S equal to -2 and S equal to -5, and there are no zeros, no need to talk about the zeros now. Okay, so this is a RC ladder. This is a RC ladder because there is no pole at 0 or infinity, which is a condition, and zeros are not there. Okay, zeros if present should be in the left half of S. So take first P of S is 1, Q of S is distinct, it's a low pass filter, right? Now, if you see what are the poles, 2 and 5, -2 and 5. Okay. Now select capital Q of S. How we are selecting? So you are starting. So I told you Q of S should be interlacing, and its degree should be greater than small q of s. Okay, degree should be greater than or equal to. Okay, so first case we will take equal to that of the degree of capital Q of s should be equal to that of small q of s degree. So that's why I'm taking two zeros for q of two zeros of q of s. Okay, so interlacing. So here the poles are 2 and 5. So I can take capital Q of s as 1 and 3. Okay, then you will get interlacing. So, and here I am taking both the degrees equal. Okay, interlacing. Okay, so we are selecting Q of S, capital Q of S. How we are selecting interlacing, and degree of Q of S should not be less than that of small q of s. Okay. Both these conditions are satisfied. This one. Then small q of s is this s plus 2 into s plus 5, and capital Q of s is s plus 1 into s plus 3, and this is your driving point impedance Z11. Okay, Z11 is this. Okay, now Z11 is this, and this is your transfer function. So now convert. So just we will try to convert this in continuous fractions. Okay, continuous fractions, so that we can get K form 1. Okay, K form 1, so that you can do it like this, right? So it's RC network. RC network. So first write it like this, and you know how to convert this given transfer function into K form 1. Okay, K form 1, convert it. Okay. So after getting this, right? So here I told you. So 1 by q of s if you have. So this network is realized by using small q of s upon capital Q of s, which is Z11 into K form 1. Okay, K form 1. K form 1, if you remember, this is this form, right? So K form 1 is this. So you just divide this and use the. So I have explained one example. Using that, you can convert. So Z11 you will get 1 by 1 plus S by 3, S by 9, this thing 9 by 5, this thing, and so on. So okay, K form 1, if you see for RC ladder, capacitors will be parallel. Okay, capacitors will be parallel and resistors will be series. K form 1, if you see. Right. So after converting this, you can write it. So starting with its impedance 1 is there. So that's why it is starting with 1 and you have a S capacitor will be there 1 by 3. Again constant you will have resistor, and again you have S 1 by SC 25 by 24 it will be capacitor. Okay, and you have constant. Finally you are ending with resistor because there is no capacitor after that, right? So 8 by 5 you have this 8 by 15. Okay, this is your KF formula. That means now 1 by Z11, right? So this thing we have divided and we have got this network. Okay, so but our problem is not complete. Okay, so we have to synthesize the net transfers. We have to synthesize the network for this given transfer function. So we have divided by this and obtained this, but we have to determine constant to determine K, constant multiplier. So our T of S is nothing but K, transfer impedance. Okay, so to get that transfer impedance constant or capital K, so here it is T of S is given as K by S plus 2 into S plus 5. Okay, it is actually if you take a constant K instead of 1, you will have T of S is K by S plus 2 into S plus 5, and this constant is obtained by using by making S equal to 0 or S equal to infinity. So we can take S equal to 0 here. If you take S equal to 0, so this was your given transfer function. Now T of S will become K by 10. Okay. If you make S equal to 0, it will become K by 10. Okay, so that is T of 0 is K by 10. Okay, right. And similarly, this is T of 0. T of 0 is K by 10 is obtained from the transfer function, right? And similarly, whatever the network we have derived, okay, we have synthesized from K form 1. For this also apply the same condition at S equal to 0. So when S equal to 0, what will happen? At S equal to 0, your reactance capacitance it will become 1 by 0 XC. XC is 1 by SC, 1 by 0, which will become infinite. So XC will become infinite and capacitor will be open. Okay. So capacitor open. So in this all circuit, so in this whatever the network you have realized, okay. So here the capacitance, all the capacitors will be open. Okay. Then you will have 1 9 by 5 and 8 by 15 3 resistors. Okay. So 1 9 by 5 8 by 15 3 resistors. And this is at T of 0, okay, because at S equal to 0, capacitors are open. Then in this case, what is the transfer function you can obtain, right? So T of 0, so our transfer function V2 upon V1 is nothing but, you can write it like, right? So it is a series network. It is nothing but this resistor upon this resistor plus this resistor or plus this resistor. You write it 8 by 15 divided by 1 plus 9 by 5 plus 8 by 15, you will get this is your transfer function at S equal to 0. So 8 by 50, 8 by 50 you got this, right? So and you from the transfer function at S equal to 0 you got K by 10 at S equal to 0, K by 10, and equate with the value you got here, right? So K by 10 is equal to 8 by 50 and K will become 8 by 5. Okay, that means you can use this network, whatever the realized network, for the given transfer function at K equal to 1 by 5, K equal to 8 by 5. Okay. That is the mean. So figure 1, what is figure 1? Figure 1 is this. Okay. So you can see figure 1 is this. So you can realize this figure 1 as a figure 1 realizes the given transfer function. Okay. So whatever the transfer function given to us is K by S plus, how much it is, S plus 2 into S plus 5 can be realized with the figure 1 with a constant multiplier K equal to 8 by 5. Okay. So this is your synthesized network. Okay. This thing. But what is the constant value? K is equal to 8 by 5. Okay. So if you observe here, what we are doing is we are dividing by capital Q of S, and Z12 is up we are for Z12, we are determining Z12 is realized with a constant multiplier K. Okay, whereas Z11, which is our driving point impedance method, okay, RC impedance method, K form 1, you have to convert it to K form 1 by continuous fraction, which is nothing but continuous divisions. By continuous divisions, you get the K form 1. Okay, and Z12 is realized with a constant multiplier. Okay, so instead of this thing, Z12, which is small p of s upon capital Q of s, okay, instead of that, we are realizing with a constant, some k. Okay, so because it's a transfer value, it is transfer impedance. Z12 is a transfer value, okay, or transfer impedance. So at s equal to 0 or s equal to infinity. At s equal to 0, what is the transfer function value? At same s equal to 0, so what is the what is the value? What is the transfer function value you are getting for the realized network? Both you compare, you will get it k value. Right, Z12 is realized with a constant k multiplier, right? Then, so which you did, so here you got k by 10 and k is equal to 8 by. Okay, so figure 1, which is nothing but this thing, figure 1 can be, it realizes the given transfer function with constant multiplier k equal to 8 by. Okay, now here what we have done is, the first case we have chosen k of s, q of s as two zeros, which is 1 and 3 interlacing. But for this transform, for this poles, one more q of s is also possible. That is, it can be 0, 1, right? Right, is 0, 1, 4, right? So 0, 4, 6, right? Not 1, because before 2, 0 you can have, after 2 you can have 4, after 5 you can have 6. So that is your interlacing. Okay, so before 2, 0, between 2 and 5, 4, and after 5 you have 6. Okay, so and the degree of capital Q of s should be greater. So you can, instead of two zeros, 1 and 3, if you take Q of s as three zeros, okay, that is s equal to 0, s equal to minus 4, s equal to 6, then in that case do the same thing. Okay, so then your Z11 will become, numerator will be small q of s, which is same 2 and 5, and capital Q of s you will get 046. Okay, 046, and take this. Okay, you will get, and do continuous divisions and try to express in K form 1, which is same, right? You get s, you get all s, right? Okay, K form 2 is 1 by gamma 1 s, 1 by gamma 2 s. This is K form 1 s. You will only get s, right? So try to get the continuous divisions and try to express it. So here it is starting with capacitor. So you have capacitor, resistor, okay, resistor, again capacitor, resistor, and capacitor finally. Okay. So in KR form 1, capacitors will be in parallel, same as it is. Previous problem also KR form 1, capacitors will be in parallel, right? So not parallel, it is KR capacitors are in admittance form type. Okay, so you have this thing. Okay, so you can write 1 by 3, 9 by 7, 49 by 25, 8 by 70, these values. Okay, now constant k. So constant k, if you take, so previously what we got, for getting constant multiplier, k by s plus 2 upon k by s plus 2 into s plus 5, s tends to 0 to k by 10 you will get. Okay, t of 0, right? T of 0 k by 10 as it is, you got for the same problem. Here what we have changed is just capital Q of s we have changed, and see, we are seeing how the what is happening if we change capital Q of s. And as s tends to 0, 1 by c tends to 0, 1 by c tends to infinity, and capacitors are open. So if you open the capacitors here, okay, if you open the capacitors here, so here you don't have any resistor, so the entire input is transferred to the output. Okay, full transmission. Okay, because you have opened all capacitors, you don't have resistor here. In this position, you don't have any resistor. We have resistors only in these series elements. Then V2 upon V1 will be 1. Okay, full transmission. Okay. So unlike the previous case, we are getting some ratio, right? R3 upon R1 plus R2 plus R3. But here, for the if you have changed Q of capital Q of S, you are getting full transmission. T of 0 is 1. Okay. So now K by 10, or K by 10 is 1. So K is equal to 10. Okay. So K by 10 is 1, K equal to 10. Okay. Now this is your figure 2. This is your figure 2. Now figure 2 realizes a given transfer function with constant multiplier K equal to 10. Right. So this is now this is your realized network. But what is the value of K? K is 10. Sorry, K is 10. So figure 2 realizes a given transfer function with constant multiplier K of K equal to 10. Okay. And this is your synthesized network. Okay. So now as Q, what we have seen is the problem is same. The problem is same, but if you have changed capital Q of S, K has also changed, and the network has also changed. Okay. Because in previous case, when capital Q of S was S plus 1 into S plus 3, okay. So your network was this, and the K value was 8 by 5. So 8 by 5. Okay. The network was this. Network element values are also different. Now, if you have taken capital Q of S, these 3 poles, 3 zeros, then in that case you are getting this form, element values are changed, and K is equal to that. Okay. So for synthesis, so it depends on capital Q of S. So okay, depends on capital Q of S, you get the network. Okay, different. So in this same problem, you can see if Q of S is changed, the final synthesized network is changing, as well as K value is changing. So this is about 1 by form. Okay, similarly, so this problem, what I discussed is it is simple. This form 1 by Q of S, right? This form 1 by S. So if you have in the numerator S or some zeros, S square, or S plus some S plus some values, okay, that is some zeros are present. That case how to obtain, you will see in the next. So this is your low pass filter. So you have resistor capacitor. So if you are taking output, and finally your capacitor is else is low pass filter. Okay. So this is about today's class. So let's take your attendance. Fine. That's all for today's class. Okay. So we'll meet in the next class. Thank you. Yes, any doubts? Yes, yes, please. Any doubts? Hello.
Awesome.
Oh, oh. Okay. I'm ending the meeting. Thank you. Thank you.